Tutorial 1, Part 2, Elements and Periodic Table. Elements are atoms with same number of protons. If number of protons is equal to number of electrons, then it is the atoms of the elements. Remember that proton and electrons have the same amount of net charges. Otherwise, the atom will have a net charge, and it will be the ion of the element. Isotopes of our element are atoms with different number of neutrons, but the proton number are still the same. Otherwise, we will not call it element or insane element. And notations for elements is shown here. A is the mass number, which is the number of protons and number of neutrons. For example, if atom have 8 protons and have 7 neutrons, then its mass number will be 15. Z is the atomic number, which is the number of proton only. And for example, if an atom have 8 protons, then its atomic number will be 8. X is the symbol for that particular element you can find in periodic table. C is the net charge, which you can determine by the following way. For example, if you have an atom with 3 protons and 2 electrons, the net charge of this atom will be 3 minus 2, and it is 1 plus for the number C. And if it has 4 electrons but 2 protons only, then it will be 2 minus, following the notation written here. If there is no net charge, for example, same proton number with same electron number, proton number is equal to 2, for example, and the electron number is equal to 2, there is no net charge, then you can just omit the C. Z is often omitted if not writing the nuclear reaction. A is also often omitted if atomic mass and isotopes is not our point of interest. This is equal to this, which is the sodium atom with atomic mass equal to 23. Because at here, there is no charge number or charge symbols. Okay, 23 sodium plus. Here, the number 1 is omitted, which means that the atom carries 1 unit of plus, or 1 unit of positive unit of charges, which therefore, by definition, which is a sodium ion. 22 sodium and 23 sodiums are isotope of sodiums because the chemical symbol are still the same, but the mass number are different. That means they have a different number of neutrons, and they are still the same element, so they are isotopes. And how can we systematically represent all these elements? We use a table, which we call it periodic table. Table is shown here, and there are several properties of this table. It is listed from atoms or elements with a smaller atomic number first. Hydrogen have an atomic number of 1, helium have an atomic number of 2, and so on. You can see that. And it is actually divided by groups, which I will introduce it in later slides. And you can find a symbol. For example, symbol for helium is here. Actually, you can just write He. How can we find the atomic number? You can see this picture, which is here. And the atomic mass you might not be see it, but it is here, which is very, very small. But in exam, they will give a much larger version of periodic table, which you can observe it and use it for calculations of questions. As I mentioned, periodic table is an arrangement of putting all atoms of elements, not ions, in ascending orders of protons, which is also the atomic number. And therefore, because elements, we consider the electrically neutral atoms, and therefore the number of electrons. Atomic number, element symbols, average atomic mass can be obtained from the table. We also introduce a new concept called atomic mass unit, AMU. 1 AMU is equal to 1/12 the mass of a 12 carbon atom. What does it mean? For example, a 12C atom will have mass equal to 12 AMU, and basically it does means that if you know the mass number of that particular atom, you can immediately find that the mass of that atom in AMU unit, which is the atomic mass unit. And 1 AMU, by definition, another definition is equal to 1 gram per mole. Mole is 1 mole is a constant, which is this huge number of atoms, because the atoms are essentially that small and it is very, very light, and we have to include that much of atoms to make up such units, which is for our conveniency in terms of the calculations. Okay, we can use the equations or the definitions from previous slide to calculate some questions. The first question is number of carbon atoms in pure 1.5 mole carbon. It is equal to this number. 1 mole is equal to this number, which is 6.02 times 10 to the 23 power, and which has another name for this value, which is the Avogadro constant. And you can just time 1.5 by this constant, and you can just get the number of carbon atoms. How about the number of carbon atoms in pure 1.5 G carbon, 1.5 gram carbon? The first, we need to find the average atomic mass for the carbon first. And because it is very, very small, and it is essentially very, very small, we just take it to 12. And the number of moles, be careful, is the number of moles of C is equal to 1.5 over 12. 1.5 is the gram, and 12, because 12 here is in terms of AMU units. AMU is equal to gram per mole, and if you 1 per bracket gram per mole, that means it will becomes mole per gram, and we just eliminate the gram, and the unit for this will be mole. The number of C, therefore, we just multiply this number by the Avogadro constant, which indicates for 1 mole how many number of atoms is within 1 mole. And how about number of carbon atoms in pure 1.5 G carbon 14? Be careful, this time atomic mass is equal to 14. And using the same step here, we get the such number of carbon atoms. Because be careful, this is different for each other because their atomic number or atomic mass is different. Periodic table characteristics. There are several periodic table characteristics I will going to introduce. The first thing is group, which is these, the vertical, or we call it columns of the periodic table, we call it groups. For elements in the same columns, we call it they are in the same group. For rows, they are called period. And for elements within the same columns, we call it they are in the same period. Group actually has a definition in terms of in chemical definition, which is elements have having same number of electrons in their valence shell, outermost electron shell, which is also normally, and or electrons in the same type of orbitals with the highest energy are in the same group. For example, for group 1 metals, they all have one electrons in their outermost shells or in their valence shell. For group 18, their outermost electron shell or their valence shell are fully filled up. And they will have very similar chemical properties within same group due to such reason. I will explain it later. Period basically is elements having same number of electron shells are in the same period. And if you still remember, number of electron shells is equal to the n, is equal to n. And n is the principal quantum number. So from the leftmost to the rightmost, the electron number increased, and it is because the proton number increased, which is in ascending order. From here to here, across a group, across from the uppermost to the lowest point, it is the electron shell in ascending orders, which means the atoms become bigger and bigger because, for example, hydrogen have only one electron shell, lithium have two, and so on. And these bracket, these rectangles represent the block within the periodic table. S is the blue one here, which have these two parts, the first part and the second part. P block, this region. D block, this region. F block, this region. And what does a block stands for? Elements indicate type of orbitals with the highest energy, which are occupied by electrons. For S block, among all occupied orbitals, S orbitals have the highest energy. For example, electron configuration of hydrogen. Hydrogen is in S block, is 1s1, and because there is only one electrons, and which means that it is very, very trivial. For helium, it is 1s2, because there is also only one type of electron orbitals, and it is also trivial. For sodium, it is also in S block, and you can see that it is the highest energy one is in 3s. For P block, we have the following similar definition. For D block, we also have the following similar definition. For F block, also. Therefore, using the block configurations or block ideas, we can very easily to find the configurations, electron configurations for all these atoms or elements. For example, hydrogen. Hydrogen is in S1. That means, and hydrogen has only one electrons, and that means it must be in 1s1. For helium, it must be in 1s2 because there is only two electrons. And for boron, it's the difference. There is some different stories. It has 5 electrons because its atomic number is 5, and because it is in p block, and that means we must know that there must have a p orbital, and it must be in the highest energy for the atoms in the p orbitals. That means that particular p orbital will be the last orbital when we try to fill in the electrons. And when the actual configurations for boron is actually 1s2, 2s2, and 2p1, and there is total number of 5 electrons when you count the numbers. And for this way, we can also find all configurations for carbon, nitrogen, and so on, because they are all in p block. For carbon, there is one more electrons, and how do we fill these 1 more electrons? We can use the configuration for boron, and because the block indicates where the highest energy electron is in which orbitals, and in this case it is p. That means the electrons must fill in the p orbitals, which is consistent with the Bohr principle, and therefore it will be in p2, and that means the configurations for carbon will be 1s2, 2s2, and 2p2, and the total number is 6. For d orbital, for d block and for f block, we have used the similar methods. And let's do the example for illustration. Determine the electron configuration of rhodium using periodic table only. There is a trick. We must first observe the position of rhodiums at element block. And for any possible atoms or elements within the periodic table, X is equal to the noble gas configuration, just smaller than X in terms of number of electrons, or which is also equal to in terms of the atomic number, plus the valence shell configurations. Valence shell configurations, as I just said, you can determine it using the which block the element is in. Periodic table. Let's first find the rhodium, which have a atomic number of 45, which is here. The closest noble gases, which the noble gases are always in the rightmost of the periodic table, which is here. Rhodium, if you still remember, if we count it leftwards, let's say for this direction, there is a decreasing number of electrons. So this one have less electrons, just less by 1 compared to rhodium, and so on. And therefore the nearest one will be krypton. 36, have an electron of 36. For noble gases, their valence shell are fully occupied by electrons. And using the blocks here, and you can find the electron configurations. And for krypton, we find the nearest noble gas configurations for krypton, although it is already a full gases. By this way, we count it this way, and we actually find it will be the argon. And then we just count it again and again, we will count it to the helium. Helium has a very trivial electron configuration, which is 1s2, and we just add it back. Helium is 1s2, and neon has 8 more electrons than helium. Helium has the electron of 2, which is specified by here. Neon has an electron number of 10. That is, add 8 more electrons to helium. And you can see the period is here, period 2. That means the additional 8 electrons will all within the electron orbitals having n equals to 2, because n equals to 1 is already filled up by the definition of the noble gases. And for 2, there is 2 types, 2s2 and 2p6, which is exactly 8. And that means for neons, the electron configuration is 1s2, 2s2, and 2p6. And by this way, for argon, we have the similar methods. And that means for argon, it is 1s2, 2s2, 2p6, 3s2, and 3p6. For krypton, we use the same way. And in this time, the n equals to 4. And there is d orbitals, as shown or as indicates by the d block presents here. And you can also use the 2n square methods to determine the maximum number of electrons which can be filled in for each distant value of n. Which is this I have already mentioned for this part. For rhodium, or we just add it back, helium is equal to this way, neon is just basically this one, argon is just basically this one, krypton is just basically this one. For rhodium, there is 9 electrons left, or 9 electrons more than krypton's electron number. And how can we arrange it? We can observe it by the blocks. And using the block concept, we find it the rhodium is equal to this one, the electron configuration. And we can also write it as this way.